Before we try to solve an exponential inequality, we need to think about the kind of moves that we can use in solving exponential inequalities. Now, we have three kinds of moves for solving equations. We have the basic moves that we used for the linear stuff: add, subtract, multiply, divide on both sides. We can treat it as a polynomial equation, whether it's a polynomial equation or something that we can pretend is polynomial, and factor it. Or we can rewrite the equation using some kind of inverse, which is what we've been doing for exponentials all along. When we're working with inequalities, we have to pay special attention to exactly which moves we're using, because sometimes some of these moves reverse the inequality symbol. Among the basic moves, multiplying by a negative number reverses the inequality sign. When we factored polynomials, we went through that whole detailed sign analysis on the number line. We haven't talked at all about what happens when we rewrite our inequality using some sort of an inverse. We've done it, but we haven't really talked about it. The last time we talked about applying some sort of an inverse to an inequality was way back when we were solving absolute value inequalities. And when we did that, we had to think about the number line and think about how absolute value is small, means close to zero, so that's going to be between two things. Absolute value is large, means it's far away from zero, so we're going to end up with something with a gap in it. And the reason that we had to think about that, the reason we had to think in pictures, is that the absolute value function might be either increasing or decreasing at different places in its domain. Those are new terms. What do I mean when I say a function is increasing or a function is decreasing? If it's increasing, a bigger input gives us a bigger output. So if A is greater than B, f of A is greater than f of B, and the other way around. A function is decreasing if a bigger input gives a smaller output. So if when A is greater than B, f of A is less than f of B, the larger input gives the smaller output, and vice versa. So if I have a smaller output, it came from a bigger input. And we can see some simple examples of this. Right? The function where we just multiply by 3, that's an increasing function. Because if I take a bigger number and multiply it by 3, I get a bigger result. And if I get a bigger result when I multiply by 3, I must have started with a bigger number. So that's increasing. Multiplying by 3 does not reverse the inequality. Multiplying by -2 is a decreasing function. Right? If I take a bigger number and multiply it by -2, I get a bigger negative number, which is less. So if A is greater than B, -2A is less than -2B. So this function multiply by 3 that does not reverse the inequality is an increasing function. This function multiply by -2 that does reverse the inequality is a decreasing function. And that's what we need to have in mind when we're applying an inverse to both sides of an inequality in order to solve. We can apply any function we like to both sides of an inequality. If the function is increasing, the inequality sign stays the same. If the function is decreasing, the inequality sign reverses. And if it does both, if it goes up and down and up again or something like that, Then we have to split things up. The way that we did for the absolute value. So we might think about the number line. We might just split up the domain and see what happens on the various parts of the domain. Fortunately, that third case won't come up with exponentials, because the log function is either increasing everywhere if the base is greater than 1, or decreasing everywhere if the base is less than 1. So if we take a log in a base greater than 1 of both sides of an inequality, the inequality sign stays the same. If we take a log in a base less than 1 of both sides of an inequality, the inequality reverses.